This is a smoothly running manufacturing line. Every finished item passes inspection, yet right next to it sits a growing mountain of discarded scrap material. A quality management system, or QMS, acts as a multi-layered framework, orchestrating how an entire organization builds and maintains its operational standards. Within that framework, quality control, or QC, plays a very specific, limited role. Its only job is to maintain the current status quo. Quality control functions by evaluating actual output against a preset goal. When a machine drifts out of calibration and defect rates spike, QC catches the error and triggers a reaction to fix the immediate problem. But because QC is entirely reactive, it ignores the baseline itself. To actually eliminate the scrap pile, a separate mechanism is required: quality improvement. Quality improvement is the deliberate, systematic disruption of how things currently operate. Its mandate is to tear down the accepted baseline and engineer out the waste that was built into the system from the beginning. Relying solely on quality control traps an organization in an endless cycle of firefighting daily errors. You spend all your resources making sure the system doesn't get worse, which ensures it will never get better. The distinction between maintaining a system and improving it was formalized by Dr. Joseph Juran, who structured these concepts into the Juran trilogy. The trilogy divides the pursuit of quality into three interconnected processes: quality planning, quality control, and quality improvement. This chart visualizes how those processes interact. The y-axis tracks the cost of poor quality, the financial drain of defects and waste, over time on the x-axis. This high, thick horizontal band is the operational baseline, representing business as usual. When an unpredictable error causes a sudden spike above this band, that is sporadic waste. Quality control steps in, identifies the deviation, and pushes the line back down into the acceptable zone. The area under the curve, the thick baseline zone itself, represents chronic waste. This is the accepted daily inefficiency that quality control is blind to because it falls within the designated operating limits. Quality improvement is the engineered force that drives the entire band downward. It establishes a new, significantly lower baseline, achieving a permanent breakthrough in performance. Because these breakthroughs require concentrated resources, they must be aggressively targeted. Management directs these efforts toward the organization's critical success factors, the key value creation activities defined back in the quality planning stage. True optimization happens here. It requires looking past the daily fires and attacking the structural waste hiding in plain sight. Once an organization identifies its chronic waste, it has to decide how to dismantle it. There are 4 distinct strategic approaches to execute an improvement project. The first is repair. This is a short-term, immediate fix applied to broken outputs to stop the immediate bleeding. The second is refinement. This involves incremental, continuous adjustments designed to tune and optimize existing processes. The third is renovation. This requires major structural overhauls of legacy systems that are severely underperforming. And the fourth is reinvention. This means abandoning the old system entirely to design an entirely new process from scratch. Correctly diagnosing the scale of the chronic waste is the first step. It dictates whether an engineering team uses a scalpel to refine a process or a sledgehammer to reinvent it. Continuous improvement, often called Kaizen, is executed through strict mathematical algorithms. These iterative models trace back to the physicist and statistician W. Edwards Deming. Deming popularized the Plan, Do, Check, Act, or PDCA cycle. It serves as the basic logical loop for testing hypotheses and solving problems empirically. Over decades, this basic loop evolved into Six Sigma, a highly disciplined, data-driven framework focused on identifying and eliminating process variation. This flowchart maps DMAIC, the Six Sigma algorithm used to refine existing processes. The steps advance linearly: define, measure, analyze, improve, and control. For complete reinvention, the path splits to DMAVD: define, measure, analyze, design, and verify, building an entirely new process from scratch. Both algorithms share a strict underlying rule: root causes are diagnosed entirely through data, stripping intuition and guesswork from the equation. Without these rigorous frameworks, improvement efforts devolve into unstructured trial and error, leading to high failure rates. At the tactical level, the DMAC engine requires raw inputs gathered during the measure phase. To format this data, engineers rely on the 7 basic quality control tools, a universal graphical language that makes complex information instantly readable. This chart is a histogram. It takes hundreds of chaotic, raw data points and sorts them by frequency into vertical bins. This instantly visualizes the central tendency of the entire dataset, revealing a clear left skew distribution. Recognizing a skew, or an isolated outlier in a histogram, proves that an underlying process has a mathematical bias. It shows exactly where a machine or workflow lacks the capability to meet its target. Once the data is measured, teams move to the analyze phase. Here, they use tools like FMEA, Failure Mode and Effects Analysis, for predictive diagnostics. FMEA forces a team to systematically break down every step of a process to predict exact failure points long before they actually manifest on the factory floor. This matrix shows how FMEA calculates risk. It grades 3 factors: the severity of the impact, the probability of occurrence, and the likelihood of detection. Multiplying these together generates a risk priority number, isolating exactly which failure mode demands immediate intervention. In an industrial setting, a machinery FMEA evaluates equipment reliability. It identifies exactly where to install automated fail-safe logic to prevent catastrophic assembly line downtime. In digital environments, a system FMEA stress tests software interfaces and integrations, highlighting vulnerabilities before code is ever deployed. Tools like histograms and FMEAs strip emotion and office politics from the process. They transform subjective complaints into highly targeted mathematical engineering objectives. Solving the problem brings the team to the final and most vulnerable phase of the DMAIC algorithm, control. There is a law of entropy in business. Without engineered constraints, a newly optimized system will inevitably drift back to its old, inefficient baseline. To hold the gains, organizations must install rigid operational mechanisms. This means writing new standard operating procedures, creating visual workplaces, and implementing continuous statistical process controls. Returning to the Juran trilogy chart, we see what this phase accomplishes. The new, lowered cost of poor quality is locked in place by strict control limits. This fully optimized process is then officially handed back to the quality control team, whose job is to maintain this new standard every single day. Achieving an engineering breakthrough is mathematically worthless if the organization lacks the systematic discipline to permanently anchor it. These localized engineering improvements do not happen in a vacuum. They form the foundation of an enterprise-wide strategy called Total Quality Management, or TQM. The core mandate of TQM is that quality is not isolated to an engineering department. It requires the active, daily participation of every layer of the organization. TQM operates as a continuous feedback loop. The empirical data and the hard lessons learned from the DMAIC process flow directly back to the executive level, informing the quality planning phase. This loop ensures the next generation of goods are engineered using quality by design. By baking the data into the earliest stages of development, the company avoids producing the chronic waste of the past entirely. Quality improvement is the empirical engine of a business. It takes theoretical strategic intent and hammers it into maximized efficiency and concrete customer value. In modern operations, quality is defined by the unrelenting, mathematical pursuit of a perfection that can never be reached, but must always be chased.